Welcome to this lecture series in group theory. Let us recall a few things that we need for this lecture. So we defined a subgroup of a group G, a subgroup N of a group G as normal if any of these three equivalent conditions are satisfied. These two things I'm sure we understand. So what is G and G inverse? G and G inverse is just a notation for this set, right? And the last one, this thing is the notation for that particular subset of the group. So these three conditions we saw. And finally, the reason for doing all this was to generalize the behavior of the kernel. So the kernel of group homomorphism had the property that G mod kernel admitted a natural group structure, natural in the sense that this projection map, which is G going to the corresponding coset of the kernel, becomes a group homomorphism. So we just wanted to mimic that property to an arbitrary subgroup and figured out that there is a certain, any of these three conditions are sufficient and necessary for that to occur. So normal subgroups of a group are precisely those subgroups for which this has a group structure with the property that the natural projection map is a group homomorphism. Okay? Right, so now let us see the problems. This is marked as star and dagger both. So this is marked as star because I'm going to sort of use this, and dagger because this we will revisit later, and this is sort of a theorem that is very important. It says that every group can be realized as a subgroup of some symmetric group. So when I say realized as a subgroup, I mean there is an injective group homomorphism into some symmetric group. That's what I mean. And this exercise shows that. It's very easy. All the steps are given. So it's a nice guided exercise. This I've also marked as star. It is a very simple fact. So it just says that isomorphisms take subgroups to subgroups, and that's it. Basically, a given subset is a subgroup if and only if its image is also a subgroup under a given isomorphism. All right. So now let us get started with the material of this lecture. Basically, this lecture is about the properties of normal subgroups. So here is the first property. A subgroup H of a group G is normal if and only if it is the kernel of some group homomorphism. So we already know that kernels of group homomorphisms are normal subgroups. That is what motivated the notion of normal subgroup. So that direction we won't be doing. We want to do the direction which shows that any given normal subgroup appears as the kernel of some group homomorphism. So that's also very easy. So let H be a normal subgroup. Then consider the natural projection map. And what is the kernel of this map? Kernel of pi is those things in the group G which map to the identity of the quotient group, but the identity of the quotient group is the image of the identity of the parent group, and not the parent group. Image of the identity of the domain of pi, because pi is a group homomorphism. So it is those elements in the group G such that this is equal to H, because what is the image of EG? The image of EG is H itself. So therefore this is the identity of the quotient group. And this implies that it's those elements in G which actually lie in H, which is equal to H. So the kernel of pi is precisely H, and we have proved this lemma. The next lemma says that the intersection of two normal subgroups is also a normal subgroup. So we can do it in two ways. First, let me do it in a sort of more pedestrian way. So fix little g in capital G. Then what we want to do to show normality is that we want to show that this thing is contained in the intersection of n1 and n2. But clearly this is contained in this guy, simply because this is contained in that. So this is contained in that. And it is therefore also contained in the other guy, and hence their intersection. Right? But what is the first one? The first one is precisely n1, and the second one is precisely n2, because n1 and n2 are normal. This implies what we have shown is that Gn1 intersection n2, G inverse is contained in n1 intersection n2, and this implies that n1 intersection n2 is normal. So that's one way. The other way is something that I like much better. So we will use the previous lemma. So we can find homomorphisms phi1 and phi2 into some groups h1 and h2 such that kernel phi1 is n1 and kernel phi2 is n2 by using the previous lemma. And now just consider this map, little g going to phi1g comma phi2g, and verify that this is also a group homomorphism. So once you verify phi as a group homomorphism, verify that kernel of capital phi, this is equal to intersection of the kernel of phi1 and phi2. Both of these checks are trivial, so I won't be doing it. And therefore, kernel of capital phi is nothing but n1 intersection n2. And therefore, n1 intersection n2 appears as the kernel of some group homomorphism, and hence by the previous lemma is a normal subgroup. All right. This is another very useful one. Every subgroup of an abelian group is normal. So suppose G is abelian and H is some subgroup of G. We want to show that H is normal. So fix little g, then GH G inverse is nothing but, by definition, this guy, which is equal to H G G inverse, where we use the fact that G is abelian. Any two things in G commute. So we have this is equal to H, and therefore GH G inverse equals to H for all G, since G was arbitrary, and this shows normality of the subgroup H. So this can be used for inductive arguments. If G is a finite abelian group and we want to show that it has some property, then it many a times one can do is find a reasonably small but non-trivial subgroup of the group G, consider the quotient group G mod H, by induction assume that the property holds for this guy because this is a smaller sized group and again abelian, and then somehow lift this property to the original group that we were intending to prove the property for. So we will see an example of this in some later lecture, and when this method will be clearer. All right, so this says that the image of normal subgroups under surjective group homomorphisms, so this is important, image of a normal subgroup under a surjective group homomorphism is also a normal subgroup. So how do we do it? Perhaps I could, yeah, maybe not. Anyway, so let me do it in a pedestrian way. So let little h in capital H be fixed. We want to show that H phi n H inverse is contained in phi n. Right, this is what we want to do. So by surjectivity of phi, we can find a little g such that this is equal to h. And now we have g and g inverse is actually equal to n because n is normal. This implies phi g phi n phi g inverse equals phi n. Why is that? Because what I'm saying is that phi of g and g inverse equals, by definition, phi of g x g inverse x in n, which is equal to phi g phi x phi g. Okay, let me write an inverse here, x in n. This is equal to phi g phi n phi g inverse. So that's what we did. From here to get there, we just applied phi on both sides and we got that. But this thing is nothing but that. We can take the inverse outside, just some properties of group homomorphisms that we proved. And therefore, what is the right hand side now? The right hand side is nothing but h phi n h inverse. Sorry, that was the left hand side. All right, so this proves that phi n is normal. So we use surjectivity to find a little g. Otherwise, this wouldn't be true. Okay. So this is a cousin of it. It says that pre-image of a normal subgroup under group homomorphism is normal. Here we don't even need surjectivity. So fix little g and h in the preimage, then phi of GHG inverse. What we want to do is show that GHG inverse is actually here. So we want to show that this is an n that's equivalent. So this is equal to phi g, phi h, phi g inverse, which is by the fact that n is a normal subgroup of the group H, this thing belongs to n. All right, let me not skip that step. So this belongs to that, because phi h belongs to n. H was chosen in phi inverse n, so phi h belongs to n. So we have that. But now we use normality to deduce that this is equal to phi g. This is equal to n by normality of n, and therefore what we have shown is that phi gh g inverse belongs to n, which is as good as saying that gh g inverse belongs to phi inverse n. And since this is true for each little h chosen in phi inverse n, we have this containment. And that's it. This shows that phi inverse n is normal. So that's one way. But I think one can use the kernel of group homomorphism lemma, which was the first lemma that we showed. So I think this should also work. So we have this group homomorphism, and suppose n appears as the kernel of some homomorphism psi mapping into some group K. So kernel psi is n. What is the kernel of the composite? This composite is psi composed phi. So kernel psi composed phi is those things in the group G, such that psi of phi of G is identity of K, which is those G in capital G such that phi G belongs to kernel of psi, but kernel of psi is assumed to be n, which is equal to phi inverse n. So that's it. So we see that the kernel of the composite is nothing but the preimage of the group n. Anyway, this was a trivial implication. So the upshot is that you can actually realize phi inverse n as the kernel of some group homomorphism, and that's also one way to prove that it is a normal subgroup. Again, I like this better than all this computation. Okay. Oops. Yeah, this is another very useful one. The center of a group is always a normal subgroup, right? So fix some little g, and let z be chosen in the center. So it is enough to show that this thing is also in the center. But what is this thing? By the fact that z in the center, z commutes with everything. So it in particular commutes with g. So this is equal to z. Right? Therefore, it is in the center. It was chosen in the center. So what we have seen is that the g inverse is contained in zg. In fact, we have shown it's equal to zg, and therefore zg is normal. That's it. So this also comes useful in proving things about finite groups. If you know somehow that the center is non-trivial, but also, yeah, if you somehow know the center is non-trivial, it can help prove things about finite groups. We'll see applications of it later. Okay. So now we want to show that, figure out a criterion to decide when a subgroup generated by a subset is normal. And for it, this is a simple lemma. This has nothing to do with normality, the lemma that I'm going to show. And there are at least two ways to do this, but I will do it in a way which I consider non-pedestrian. Okay, so what does it say? It says that fix a group G and fix a subset of the group, then this equation holds. So this is called a conjugate, this kind of thing. So the conjugate by G of the subgroup generated by S is same as the subgroup generated by the conjugate of S. It's a nice statement. So let's get on with it. So fix some little g, and we want to show this conjugation statement. So define phi sub g from g to g as phi gx equals gx g inverse for all x. And by the exercise that I have star marked, we know that phi g is an isomorphism. Okay. Right. So now let A be those subgroups of G that contain S, and B, this fancy B, and the first one was fancy A, the second one is fancy B. Fancy B is all subgroups of G that contain GSG inverse, but realize that GSG inverse is nothing but the image of S under phi G. Right. Okay. So these are our script fancy A and fancy B. And here is the thing, that if you consider this map, which takes H to the conjugate, this is a bijection. Call this map whatever you want, let's say capital phi. Then this is a bijection. So why is it a bijection? So first of all, if you pick some subgroup which contains S, then its image under phi G, this is the image of H under phi G, it will of course contain the image of S under phi G. So this thing will contain GSG inverse, and this will also be a subgroup, because image of a subgroup under a group homomorphism, in fact, is a subgroup. So at least we have, this is a legitimate map from A to B. And since phi G is an isomorphism, you can just do the reverse thing also. So just I leave you to check that this map capital phi is actually a bijection. And the second star mark problem may come useful here, but that problem is a triviality, so you don't even need to look at it. So this is a bijection, and therefore then this intersection, what is this? This is precisely the subgroup generated by S. That is the definition of the subgroup generated by S, because the subgroup generated by S is the quote-unquote smallest subgroup of the group G which contains S, and that is the intersection of all the subgroups that contain S. So this is equal to subgroup generated by S, and this implies the image of this under phi G. So phi G of intersection H in script A, this is equal to image of phi G, image of subgroup generated by S under phi G. But this left hand side is nothing but that. Now this implication is an easy one, and I leave this as an exercise. All one needs to do is pick an arbitrary element here and show that it is here, and then pick an arbitrary element here and show that it is here. That will show that these two things are equal. But basically this is more like a set theoretic fact than a group theoretic fact. But anyway, so I leave this for you to check. The crucial fact here is that phi G is a bijection, if you want to look at it as a set theoretic fact. Okay, so we have that, and now we use this bijection. So what this left hand side is also equal to capital phi of H. That's how the map capital phi was defined, right? So this is equal to phi G of the subgroup generated by S. But since capital phi is a bijection, this is also equal to that, right? So what is this left hand side? The left hand side is the intersection of all the subgroups of G which contain this guy, and therefore this is the subgroup generated by, I don't have space, but let me, so this thing is the subgroup generated by phi G of S. So this is equal to that, and that's precisely the statement of the lemma. All right, so this may look like a complicated thing, but it is not. All we are using is the fact that, well, the definition that the subgroup generated by S is the intersection of all the subgroups which contain S, and just exploiting the fact that this thing is image of an isomorphism, which is this isomorphism. That's all we are doing. You can work it out for yourself, but this is a full argument. All right. Now this gives us a criterion for deciding when a subgroup generated by a particular subset is normal. So G be a group and S be a subset of it. And suppose this happens for all little s in capital S, then the subgroup generated by S is a normal subgroup. Okay. So let G in G be fixed. And we want to show that this thing is contained in that. This is what will show normality. So we have this guy is equal to, by the previous lemma, that guy. But this is contained in the subgroup generated by the subgroup generated by S. So I need to explain that. The reason is this thing is contained in the subgroup generated by S because of this condition. So this condition is basically saying, this condition is saying that, I mean, I should have written it that way perhaps, that this thing is contained in the subgroup generated by S. That's exactly what that is saying. So this guy is contained in the subgroup generated by S, and hence the subgroup generated by it is contained in this thing that we have written. But this is equal to the subgroup generated by S. Why? Because this is already a subgroup. The subgroup generated by a subgroup is the same subgroup. All right. So we have shown the containment that we wanted. So G, that thing is contained in that, which implies this is normal. So this is one way to decide if the subgroup generated by a set is a normal subgroup. Okay. So this is an interesting concept, the commutator. Fix a group and take this set of all commutators. Such a thing is called a commutator in G. So basically you take any x and y, any two elements of the group G, and consider this particular element of the group. This thing is called a commutator. And this is also written as, this thing is also written like that, just a bracket with x and y, because this is cumbersome to write all the time. So this is just a notational difference. Okay, and now the commutator group is defined as the subgroup generated by all the commutators. So this guy is the commutator of G. Okay, and we want to show that this is normal, that this guy is a normal subgroup of G. So we will use our previous lemma. So let little s in S and fix little g in capital G. Want to show that we will, or rather will show that that GSG inverse is again in that. So this will show normality by the previous lemma, but GSG inverse equals, this is a little bit of a trick, SS inverse GSG inverse. All we did was just multiply with an identity and wrote identity in this way. But this is equal to little s into S bracket G inverse, right? That's the definition of the bracket. And this of course lies in the subgroup generated by S. Why? Because this is already in S, or okay, I should say this is already in the subgroup generated by S because it is already in S. And this is also in the subgroup generated by S because this is a commutator. This, S is all commutators, and hence this is in S, and hence in the subgroup generated by S. So if these two things are in the subgroup generated by S, their product is also in the subgroup generated by S. So that's it. And this implies normality of the commutator subgroup by the previous lemma. So the set of all, the commutator subgroup is a normal subgroup, and this is useful many times because this quotient is an abelian group. So since commutator subgroup is a normal subgroup, the quotient has a group structure, a natural one, and we want to show that that guy is abelian. Okay, so let us write x bar. This is just a notation. So we will write x bar to mean, so for x in G, so let x be an element of G. X bar denotes this particular coset because that's easier to write. Okay, so this is the notation that we develop, and now let x and y in G be arbitrary. Want to show that x bar y bar equals y bar x bar. Right, this is what will show the abelianness of the quotient group. So once we realize that, this is equivalent to showing that x bar y bar, or maybe I should write y bar inverse x bar inverse x bar y bar is equal to E bar. E is the identity of G. So that's what we want to show. But x bar inverse y bar inverse x bar y bar equals x inverse bar y inverse bar x bar y bar, which is equal to x inverse y inverse x y bar, which is equal to the bar of that. But this guy is already lying in the commutator group, and therefore this is E bar, and that's it. That's what we wanted to show. Right? So we wanted to show that, and that's what this is. So the quotient is an abelian group. Okay, so let me end with a non-example. I will not be doing the computation because this is just a matter of computation. Fix this group S3, which is the symmetric group of this particular set. D be this particular group. So we have the group G cross G, but we take a subset of it, which is sort of like the diagonal. And one can easily show that this is a subgroup. And then one can show that this is not a normal subgroup. So as a matter of pure computation, one can show this. So not all subgroups are normal is all that I wanted to say with this example. Okay, so as usual, like, comment, share, subscribe. Also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.